As skyscrapers get taller, making sure that they stay stable in high winds or in the event of an earthquake is increasingly important. Thankfully, physics has come to the aid of civil engineers and architects across the world in the form of the tuned mass damper. I am Amy Wells, and today I'm going to be looking at the basics of a tuned mass damper and how it works. What is a tuned mass damper? A tuned mass damper is a system, sometimes referred to as a TMD, whose primary purpose is to dissipate energy. The energy input into the system could be factors such as wind or from factors like seismic waves. There are a few types of tuned mass dampers that have developed over the years. The first designs were translational mass dampers, which used a series of springs and rollers to dissipate energy in a single axis. These singular axis designs have slowly evolved into the modern versions of these designs, which function in multiple axes simultaneously. Another type of tuned mass damper is the pendulum tuned mass damper, which I prepared a model of today, where it has a mass suspended on a string or rod. Now, you are likely wondering, how does a tuned mass damper work? How do they tune it, and what is it tuned to? What magic is responsible for the slowing of the building? Well, tuning a mass damper is a simple matter of changing the length of the pendulum. For my model, I've determined 2 points. At one point, the period is 1 second, and that has a length of approximately 25 centimeters. And at the second point, the period is 0.75 seconds with a length of approximately 14 centimeters. As seen, the longer pendulum has a longer period, and this confirms the expected relationship of L, being the length of the pendulum, is equal to the gravitational acceleration, noted as g, over the square of 2 pi over the period, noted as t. The frequency of a TMD is typically tuned to either the resonant frequency of the building, that being the frequency at which the displacement or acceleration is greatest, or to another frequency that is otherwise important but difficult to dampen with conventional methods. The mass of the damper should also be carefully considered, but that is beyond the scope of this video. The next factor to consider is the damping ratio. The damping ratio is the rate at which the tuned mass damper removes energy from the system, or the magic responsible for the slowing of the building. When it is 0, there is no damping in the system, and the system will oscillate infinitely. While between 0 and 1, it is considered underdamped. At 1, it is critically damped, and while it is greater than 1, it is overdamped. Damping ratios between 0 and 1 are most desirable due to the comfortable rate at which the energy is dissipated. Rates greater than 1 can lead to uncomfortably fast dampening. The physical process of dampening is quite like that of destructive interference. For those who are unfamiliar, is what occurs when two waves that are perfectly out of phase with each other collide. The resultant wave, as determined through the additive properties of waves, is perfectly flat as the energy of the two waves has been perfectly cancelled out. Now, with a basic understanding of destructive interference, we can look at the physical model I prepared to help explain these concepts. I'm going to apply an initial force displacing the structure to the right, and when I release it, we see that the pendulum continues to follow the roof. If we look at the forces more closely, we can see that the force of the pendulum and the force of the roof are counteracting each other. As the pendulum goes away from equilibrium, it's exerting a force back to equilibrium, and then as the building extends from equilibrium, due to velocity, it is applying a force in that direction. These forces cancel each other out as destructive interference. Another way in which we can view these forces is by instead putting the pendulum into motion. Releasing it, we see that the building is once more oscillating, however now, pendulum is the one exerting the force on the structure, and the structure itself is dampening the energy. The damping ratio of my design is controlled by this screw at the top, and if we loosen it, the damping ratio will decrease, and it will take longer to be dampened. One thought you might have is what would happen if the pendulum and the structure were in phase with one another. This cannot happen due to the way in which the pendulum is initially excited. It has to be excited by the displacement of the structure. It itself cannot be excited as its only connection is through the structure, and it inherently will always be out of phase because of that. I hope this video has been helpful in demystifying the neat technology of tuned mass dampers. If you want to read more yourself and delve deeper into the interesting mathematics behind tuned mass dampers, I've included the links below in the description. I have been Amy Wells, and I'll see you next time.